Suppose T is a function that maps vector space V into vector space W. V is the domain of T and W is called the codomain of T. If V is in the domain and W is in the codomain such that TV is equal to W, then W is the image of V under T. The set of all images of vectors in V is the range of T, and the set of all vectors V in V such that TV is equal to W is called the preimage or inverse image of W. Basically, we have the domain, we take values, vectors from the domain, and T maps them into elements like W. It forms the range, which is a subset of the codomain. We have a theorem here. The range of T is a subspace of W. The range of a linear transformation like T that maps V to W is a subspace of W. So basically the kernel is a subspace of V and the range is a subspace of W. Remember that if T is a linear transformation that maps N space to M space such that Tx is equal to Ax, A is the matrix representing this linear transformation, then the kernel of T is equal to the solution space of Ax equal to 0. The null space of A is also called the solution space of the system Ax equal to 0. And recall that if A is an M by N matrix, then the set of solutions of the homogeneous system of linear equations Ax equal to 0 is a subspace of Rn, the very first set. And it's called the null space of A, and it's denoted by N of A. N of A is equal to the set of all vectors in the N space such that Ax is equal to 0. The dimension of the null space of A is the nullity of A. So this is what we learned before. Now we are switching to linear transformations. We can talk about the rank and nullity of a linear transformation now. Let T from V to W be a linear transformation. The dimension of the kernel of T is called the nullity of T, and it's denoted by nullity, open close parenthesis T. The dimension of the range of T is called the rank of T. It's denoted by rank, open close parenthesis T. As we saw before, if you add the rank and nullity is equal to N. Let T from V to W be a linear transformation from an n-dimensional vector space V to a vector space W. Then the sum of the dimensions of the range and the kernel is equal to the dimension of the domain, everybody. So N is equal to rank of T plus nullity of T. The proof is going to be covering the case that rank of T is equal to the dimension of the range of T, which is equal to the dimension of the column space. But the dimension of the column space by definition is the rank of matrix A. So basically, when you're talking about the rank of a linear transformation, we're talking about the rank of matrix A. And suppose we denote it by R. The nullity of T is basically the same as the dimension of the kernel of T. But remember that the kernel of T is nothing but the solution space of Ax equal to 0, which as we saw before, it is N minus R. So basically, if you add the rank and nullity of T, it is R plus N minus R. You can cancel R and negative R, which is equal to N. So now that we defined the nullity and rank of T, let's go over one example together. Question says, find the rank and nullity of the linear transformation T that maps the space to the space is defined by the following matrix. This matrix, 3 by 3 matrix, 1, 0, -2, 0, 1, 1, 0, 0, and 0. A is already in reduced row echelon form. As you can see, it has two non-zero rows, the very first row and the second row. So the rank of this matrix is equal to 2. Since you have the rank of the matrix equals to 2, it means that the rank of T is equal to 2. So the nullity, which we know is the dimension of the domain minus the rank, is equal to 3. Again, 3 is your n. The dimension of the n space, which is 3 minus the rank, which is the number of non-zero rows, equals to 1. So the nullity is equal to 1. So if you have a matrix, make sure to write it in reduced row echelon form, find the number of non-zero rows to basically find the rank of T. Finding n is very easy, right? N is basically the dimension of the domain. Then do the subtraction to find the nullity. Suppose T is a linear transformation that maps the 5 space to the 7 space. Find the dimension of the kernel of T when the dimension of the range is equal to 2. Well, the dimension of kernel of T is n minus the dimension of the range. Well, we know that n is equal to 5, everybody. N is the dimension of the domain. 2 is the dimension of the range. So we already know what is the dimension of the kernel of nullity. Why is that? Because just 5 minus 2 is equal to 3. The calculation is very easy here. Find the rank of T when the nullity of T is equal to 4. Let us take a look at the work. Rank of T is equal to n minus the nullity of T. So what is n? N is equal to 5. What is the nullity? Nullity is given to us as 4. So just substitute that here. 5 minus 4 becomes 1. Part C, find the rank of T when the kernel of T is equal to 0. Ooh, that's an interesting case. In this case, the nullity of T is equal to 0. So the rank of T, which is defined as n minus nullity, is 5 minus 0, or 5. So it happens that the rank of T and the dimension of the domain are equal to each other. So we went over different cases, different scenarios to calculate the rank and nullity for this linear transformation that maps the 5 space to the 7 space.